Welcome back, everybody. It's my great honor to introduce the first keynote speaker of today of the conference, which is Vladlen Koltun. And this is a video that will be streamed to all sessions in parallel. Vladlen Koltun is the chief scientist for intelligent systems at Intel and directs the Intelligent Systems Lab, which conducts research in computer vision, machine learning, and robotics. He obtained his PhD in 2002 in theoretical computer science at Tel Aviv University. From 2002 to 2005, he was a postdoc at UC Berkeley and then became an assistant professor at Stanford University, where he switched his research direction to visual computing, which he is doing today. He won numerous awards, including the NSF Career Award and an Outstanding Student Paper Award, one of the most notable awards at NeurIPS in 2011. One thing that's very special about Vladlen is that he's very diverse. He's known for many big contributions in diverse areas, including vision, graphics, and robotics. Just to name a few of his most well-known contributions that you are probably familiar with. He contributed the dilated convolutions to the deep learning community and the efficient, fully connected conditional random fields. He also worked on the direct sparse odometry, which is one of the state-of-the-art odometry systems today. He and his team, in collaboration with his collaborators in Barcelona, also developed the popular Carla driving simulator. He also worked at the intersection of synthetic and real data. He produced a big synthetic ground truth data set with photorealistic data using the GTA 5 simulator. And he worked on core robotics and learning problems, including guided policy search. So I'm really looking forward to Vladlen's talk today. He will tell us something about how we can attain photorealism. And the video will be streamed because Vladlen has recorded the talk before.
Hello, and thank you for inviting me to give this talk. This is a keynote talk for a joint European conference on visual computing that was scheduled to take place in Tübingen today, but due to the coronavirus pandemic and the associated disruptions, it is taking place entirely virtual. I put up this photograph of lovely Tübingen on the slide to say that it is a lovely place, and I'm looking forward to coming back and visiting it again someday. Many good friends live there. So this is our agenda for today. We're going to begin with a general introduction to the pursuit of photorealism, and then we are going to review two recent works from my lab. One is called Free View Synthesis. It is a work that was made public about a month ago and was presented at the European Conference on Computer Vision just a few weeks ago. It's very fresh, and I'm going to show you some results and review some things we learned. And then we're going to do something very special. I'm going to present a work for the first time that has never been presented outside my lab before. You're going to be the first to see this. This is called NeRF++. It is a new work and a paper that we are going to post online probably in about a week, and I wanted to do something special for you since you invited me to give this keynote, and I wanted you to be the first to see something. So this is going to be the first time NeRF++ is presented outside my lab, and you are going to be the first to see this. So let's begin with a general introduction. It's tempting to think of the pursuit of photorealism in terms of two cultures, the physics-based culture and the image-based culture. I am borrowing the term the two cultures from C.P. Snow, a novelist and scientist who wrote an essay with this name in the 50s, and it was a very important essay in 20th century intellectual life. It described two cultures in 20th century intellectual life, and the phrase has become quite well known. So we're going to apply it here to the pursuit of photorealism. And I went back 25 years for this talk and looked over the program of SIGGRAPH 1995, 25 years ago. And we see the representatives of two cultures very clearly. On the left, we see a paper by James Arvo, Applications of Irradiance Tensors to the Simulation of Non-Lambertian Phenomena. On the right, a clear exemplar of the image-based approach, QuickTime VR, an image-based approach to virtual environment navigation. Both are single-author papers. Apparently, it was easier to publish single-author papers at conferences like this 25 years ago. So we see these two different approaches to the pursuit of photorealism, and they are alive and well. We can look over the program of SIGGRAPH 2020 this year and again see very clear exemplars of these two cultures. Here's one exemplar of the physics-based culture, Langevin Monte Carlo rendering with gradient-based adaptation. On the right, we see an image-based system, immersive light field video with a layered mesh representation. And the quality of the results has come a long way. We can look at the images from 25 years ago, and we can look at the images from this year. And it's clear that significant progress has been made. And it's also clear that these two cultures are still quite prominent and very well represented. However, we can also question whether these really are two distinct cultures, whether that would be the most productive way to view them. Consider, for example, this wonderful example of photorealism. This is, in fact, an interactive real-time demo created by the Unity demo team 2 years ago that, in my view, attains photorealism. This is photorealism. This is a computer-generated, computer-simulated scene, and it, as far as I'm concerned, is photorealistic. This is photorealism. The way this has been created very strongly relies on ideas from both cultures. The scene is simulated, the light transport is simulated in a rendering engine, but the assets are created with image-based techniques. The assets are created with photogrammetry. Real images are mapped onto reconstructed three-dimensional objects to create texture maps, albedo maps, specular maps, and the representation of all the materials on all the objects here is directly acquired from images, directly acquired from reality. And we can see here the beautiful interplay of the light transport simulation in the rendering engine and the photorealistic materials, the photorealistic assets that are so critical to the photorealistic appearance of this scene. So the physics-based simulation makes the scene come alive. You see the light moving, you see the shadows. The objects are not frozen, they're animated, but the photorealistic appearance is afforded by the image-based 3D reconstruction and the image-based materials on all the objects. Here is another example that combines the two cultures to great effect. This is from a computer-generated short film by Alex Roman called The Third and the Seventh. It was created more than a decade ago. And this film, again, entirely computer generated, created in a rendering engine, completely controlled by a rendering engine. This is computer graphics, but it is photorealistic. This, in my view, again, also attained photorealism. It is a fantastic example of the kind of thing that we are striving towards. And a huge part of this photorealistic appearance is, of course, the image-based materials, the image-based assets. Of course, all the material appearance of all the objects in this scene is strongly acquired from reality. The texture maps, specular maps, the materials that you see here were taken from images, reconstructed from images. So again, the physics-based simulation makes the scene come alive. It allows us, as you could see, to change the depth of field, the camera properties, the lighting, to control the scene. But the photorealistic appearance is coming from the image-based assets, the image-based material specification. In fact, looking at these examples of photorealism that has actually been attained in computer graphics, we can argue that my title was somewhat misleading. At this point, we probably shouldn't be talking about towards photorealism as if photorealism is some kind of aspirational goal that is out of our reach. In fact, we know how to attain photorealism. We've just seen examples of photorealism. We know how to achieve photorealism. It's just that the future is already here, as William Gibson said. It's just not very evenly distributed. The challenge at this point is not to tick off the binary flag of attaining photorealism somewhere, but rather to enable the attainment of photorealism on a large scale, so that you and I, anybody who is interested, can simulate any scene that they are interested photorealistically, so that any independent game developer, amateur, enthusiast content creator can imagine a scene and then create it in photorealistic quality and simulate it with photorealistic clarity and detail. That, to me, is the current challenge. That is what we should be working towards in the coming decade or two. After this general introduction, let me proceed to tell you about two relevant recent works from my lab. And both works are going to be very much examples of the image-based culture. I do like the physics-based approach. I think it's very important, and I think the ultimate solution must come from marrying physics-based and image-based techniques, just like these beautiful two examples of photorealism that I showed you have done. So the most prominent examples of photorealism in computer graphics to date have been attained by marrying image-based and physics-based techniques. And that is what I think the solution must look like in the future as well. However, right now, the most recent and most exciting work from my lab that I can present is very strongly based in the image-based camp. If you invite me to give this talk again in a year or two, I hope to show you some more work from the physics-based side, which we are interested in and are working on, and ideally work that strongly combines ideas from these two cultures. With that disclaimer, let's talk about the two recent image-based rendering works from my lab. With a note that this general research direction is nowadays commonly referred to as view synthesis. I think of view synthesis as a clever rebranding of image-based rendering. It is a more streamlined, more memorable term, so somewhat akin to deep learning, which is rebranding of neural networks. View synthesis is more or less a recent rebranding, and not so recent, but recently increasingly popular rebranding of image-based rendering. So we can call it view synthesis. It's good. It's a good term, I think. It's a good term to use. It's shorter, it's catchier, it's more memorable, and it is correct. But we also should remember that there is 25 plus years of history in this research direction. There are important works that have been done on image-based rendering for more than 25 years now, and any student, any young researcher who is coming into this field should not assume that relevant view synthesis work and view synthesis work that they should know about started 2 years ago or 3 years ago. You really should go back to the roots and review very important and very relevant and very informative image-based rendering work from the 90s, the 2000s, and all through the 2010s. Let's start with a recent paper that we just presented at ECCV, the European Conference on Computer Vision, a few weeks ago. And this has been driven by Gernot Riegler. This is the result of a very substantial investment for an extended period of time by Gernot, in which we were trying out many ideas, and I kept coming back and saying this is not good enough, this is not realistic enough to publish. We must work harder until we attain a satisfactory level of realism, and at some point that bar has been passed. So these are input images of a scene from the Tanks and Temples data set. You can see here handheld images with Arno, who collected the Tanks and Temples data set, walking around this truck, collecting a video with a handheld camera. See, these are snapshots from this handheld video. This is a truck outdoors, completely uncontrolled outdoors environment in San Pedro Market in San Jose. It's a lovely place. You're encouraged to visit, and you can see it's a real scene outside. And here is a camera trajectory, a new camera trajectory synthesized by free view synthesis, our approach. So this trajectory takes us through a sequence of camera poses that have not been in the input. We are now going into the scene and walking around this scene freely after it has been captured with those images that I showed you. Here, free view synthesis is both the name of our technique and refers to our ambition, what we aspire to do, our goal, our aim. Our aim is to be able to walk through the simulated scene freely with no constraints. First of all, our input data should be natural, something that should be very easy for people to acquire, like handheld video sequence. This to us is the canonical form of input. You take a camera, you take your iPhone out of your pocket or your Android phone, you take a video, you walk around the scene, you image the scene with handheld video, you push a button, you wait a little while for some pre-processing to be done, After that, you can walk into the scene and just walk around the scene freely. Not just moving your viewpoint a little bit in between and near where the camera was, but really freely traveling through the scene as conventional computer graphics, as physics-based approaches allow you to do. We should strive towards the same level of freedom and flexibility that we see in conventional physics-based computer graphics. And you can see here that we've attained substantial freedom and substantial realism. The results are not perfect. There are clear artifacts. There's clearly work that remains to be done, but it's really quite good. Here are the original camera poses in green. This is where the camera was for those input images that were provided to the technique. And in red, you see the trajectory of target camera poses that was used for synthesis of this new sequence. And you can see that the red camera poses walk through the scene quite freely. They don't stick to being near the green cameras. They don't just interpolate. They really walk into the scene quite a bit away from where the camera was. They walk about a meter or more towards the truck, really walking into the scene, seeing the scene from different viewpoints at different levels of detail. It's this kind of unconstrained, free view synthesis that we are after. Well, let's talk about how this is done. This is an approach that is strongly rooted in classic 3D reconstruction. So first we do structure from motion to localize the cameras and triangulate a number of very confident anchor points in the scene. We then reconstruct the scene in greater detail using multi-view stereo. You see here a denser reconstruction. From multi-view stereo, the scene is covered in more detail, more densely, but the reconstruction is also quite noisy. Multi-view stereo can yield results that are quite noisy. And to deal with this noise, we then perform meshing. We perform surface reconstruction to reconstruct a cleaner surface that covers the scene. This surface, this 3D reconstruction, is used as a scaffold for our technique. It is used as the scaffold for view synthesis. The view synthesis itself is done by a combination of two deep networks, an encoder and a decoder. The encoder operates on each input image. This can be done in pre-processing, and extracts a feature vector for each pixel of each input image. So each input image is densely passed through an encoder, and we end up with a tensor of feature vectors per pixel for each input image. Then, given a target view, feature vectors from a number of nearby input images are projected into the target view. This is where the 3D reconstruction comes in. For each nearby source input view, the feature vectors from that input view are back projected onto the 3D reconstruction, onto this geometric 3D scaffold, and then projected into the target view. This gives us a number of such projected images with corresponding depth values, and those images are images of the features, of the feature vectors encoded by the encoder. So we have several layers of these projected, fairly dense feature vectors with associated depth values splatted into the target view. We then have this recurrent decoder that goes through these projected images of feature vectors and integrates them into a clean color image. For each projected set of feature vectors, it produces a dense color map, dense image, with associated confidence values, and then these colors and confidence values are integrated to produce a final color image, and this is the image that you see synthesized by free view synthesis. Let's take a look at some results again, and now compare to relevant baselines, to relevant recent view synthesis work. Here is a result on this truck sequence by local light field fusion. This is a technique published at SIGGRAPH 2019, and you can see that it doesn't work very well. It's really quite bad. This is primarily because we're taking this technique quite far from its comfort zone. It was designed primarily for a setting in which the input images are arranged in a nice regular grid. So maybe you have a planar array of cameras, a grid of cameras, and they take images. And then this local light field fusion lets you interpolate between the views spanned by these cameras, maybe go outside them, nearby, a little bit. This is very different from this unconstrained free view synthesis that we aim to attain in this work. So the local light field fusion technique is taken very far from its modeling assumptions. Obviously, in our case, the cameras don't lie on a grid. Far from it. It's just more of a one-dimensional trajectory in post space, a handheld, noisy camera that is really traveling through the scene, traveling into the scene over long distances, and then at test time, we really want to go into the scene and travel freely. Here's another technique published at ECCV 2019 called extreme view synthesis, quite extreme indeed. This has interesting aesthetic qualities to it. I can imagine it in an MTV video as a kind of special effect, but it is not quite what we are aiming for. This is neural radiance fields, also known as NERF. That's published concurrently with our work in the same conference, ECCV 2020. This is a very interesting work that takes a fairly radically different approach to the view synthesis problem, and I will discuss it in more detail in the second part of my talk. Clearly, it doesn't quite hit the mark, although aesthetically it again is very interesting. It produces results that are not without aesthetic appeal, but it's clearly not photorealistic, and it's a very interesting approach that we will analyze in more detail. Here again are the results of our technique, free view synthesis. You can still see artifacts. It is not perfect, but it's clearly among this set of techniques. It's clearly much closer to where we want to be, to what we are aiming for. Here is another scene from the Tanks and Temples dataset. This is the M60 scene. You see here input images, just to show you what the scene actually looks like and what kind of input was provided to the different approaches. This is one of the scenes that gives the Tanks and Temples dataset its name. It was collected in a tank museum. These are the results of local light field fusion. Here are the results of extreme view synthesis. Again, fairly interesting as a special effect. Here is the output of neural radiance fields, or NERF. You can see that it's doing something. It's not a catastrophic failure. It's not quite there, but it's clearly doing something. And here is free view synthesis. Again, there are clear artifacts in some parts of the sequence, but there are some parts that are very good, very realistic, like this. So this seems to be in a good direction. Here is a part with clear artifacts. You can see some of the wheels disappear. That's definitely very interesting to analyze, and we are working on improvements to this approach now, and we have some ideas how to ameliorate, how to avoid these artifacts. So we're not quite at perfection yet, but this seems to be a good direction, and the results are quite a bit better than the other recent approaches. Here is another scene. This is a playground scene, again, unconstrained, real-world scene, handheld video input. These are snapshots from the input video, and this is the set of input images that were used as input to all the techniques. Here is the result of local light field fusion. Here is extreme view synthesis. Here is neural radiance fields. Again, it's doing something. The results are not quite photorealistic. There are real artifacts, but it's clearly doing something interesting. It's doing something interesting that we will look into in more detail in just a few moments. And here are the results of free view synthesis. Here again, it's instructive to note that, first of all, this is just much better than the baselines. It's clearly much more realistic and sharper than the baselines. And it's also very interesting to look at the remaining artifacts and what they are due to. Look at the slide and look at the interior of the slide, and you can see that the interior of the slide disappears. You can see that it's missing in some frames. The reason it's missing is because it was not reconstructed well by multi-view stereo. The interior of this slide is a large, shiny, flat, featureless surface. And these kinds of surfaces are the kinds of surfaces that multi-view stereo fails on. Essentially, the multi-view stereo system we used did not reconstruct the interior of the slide. It's just missing in the 3D reconstruction. And free view synthesis inherits this limitation. Even though it does have some deep networks that can structurally perform in painting and could in principle compensate for this incomplete reconstruction by in-painting the slide during the decoding stage, during the neural rendering stage. This in practice is not happening here, and it's clear that here the reliance on multi-view stereo and meshing to provide a scaffold for the view synthesis is biting us. It also reveals its drawbacks and limitations. And this is again something that is instructive to think about as we think of the path forward and how we can alleviate these artifacts, make the system more robust to such limitations in the individual modules. So this provides, I think, a fairly good overview of where free view synthesis stands and where that approach stands. And now I want to talk about the second work I am presenting today, which is joint work with Kai Zhang, Gernot Riegler, and Noah Snavely. So Kai has been an intern in my lab this year, and this is his internship project, and Noah is his advisor at Cornell. And we've had a very interesting and educational time looking into NeRF, looking into neural radiance fields, thinking about modeling decisions that approach makes, and trying to understand why it works well when it does, why it fails when it does, and what we can do to make it more stable, to make it succeed more often, and to guard against some of the failure modes that we have uncovered. So our running title is NeRF++, Analyzing and Improving Neural Radiance Fields. And again, this is work that is presented for the first time. The paper is not public yet. You are the first to see this, and we expect to post the paper online in about a week. Our paper is inspired by and is a direct follow-up to this very interesting ECCV paper, NeRF, representing scenes as neural radiance fields for view synthesis. And this paper is of interest in part because it takes a radically different approach to the view synthesis problem. You saw that the free view synthesis approach that I presented was quite modular. It used classic components like multi-view stereo, meshing, surface reconstruction, these things that the community has been working on for decades now. NeRF is different and is a much more radical approach. Here is the essence of the neural radiance fields representation. Consider a ray in 3 space. A ray is a 5-dimensional construct. It has 5 degrees of freedom. 3 degrees of freedom for its origin, x, 3 degrees of freedom in space, and 2 degrees of freedom for the ray direction, d. So 5 degrees of freedom for the ray. The NeRF representation, in essence, is to estimate a function that, for each ray, computes the color and density associated with that ray. So for each ray xd, the neural radiance field estimates a color, that's 3 dimensions, RGB color, and density sigma. So in total, the output is 4-dimensional. Now, that density basically says whether there is a surface there, whether there is an object at point X or not. So ideally, if the point X falls on the surface of or in the interior of an opaque object, sigma should be 1. If X is in free space, just empty space, sigma should be 0. And if there's perhaps some participating medium or uncertainty, some fog or some translucent surface, sigma can be between 0 and 1. All right. So this output, color, radiance, and opacity, density, is associated with each ray in 3 space. So given another ray, x prime, d prime, NeRF will output a color, c prime, and a density, sigma prime, associated with that other ray. So NeRF is a function, an approximation of this radiance field, a function that maps from the 5-dimensional space of rays to the 4-dimensional space of colors and densities. And in practice, the representation is a multi-layer perceptron. So the NeRF training process approximates this latent function with a multi-layer perceptron. It fits a multi-layer perceptron to this function, and then you can, at test time, query this multi-layer perceptron with XD pairs, and the multi-layer perceptron will output an estimated color and density for any ray you give it, for any ray you query it with. Given such a NeRF, given such a neural radiance field implementation, you can synthesize images very easily. Given a camera, you trace rays out of the camera into the scene, perhaps along each pixel, and then you step along each ray. So you sample along each ray, and for each sample point, you ask, what's the density here? The density here is 0. Well, you keep going. At some point, you'll hit a very high density, density 1, and you will also get the colors associated with these points. And you simply integrate the density and color along each ray to estimate the radiance along this ray. So in an idealized setting, you may step along this ray and hit density 0, 0, 0 while the ray travels in free space, and then at some point you'll hit density 1. You'll sample, you'll hit density 1, meaning you hit an object. The ray hit an object, and then you ask what's the color. NeRF gives you the color from this point in the direction of the ray. And everything is well. You now have the color, and you know the color of that that pixel, the radiance along that ray. And the training process follows very naturally from this image synthesis process. For training, you can just hold out some image from your training set, and then use the partially trained NeRF to render an image from that same pose. The whole rendering process is differentiable. So you render an image, and then you compare to your ground truth held out image from this camera, and you attach a loss to the discrepancy, the difference between the 2 images, the generated image and the ground truth image. We've been analyzing NeRF because we've been intrigued by this approach, and by some settings in which it works well, and some settings in which it fails in surprising and sometimes really catastrophic ways. And we uncovered 3 problems, 3 issues with the NeRF approach. The first is what we call the shape-radiance ambiguity. The second is something that we refer to as the near-field ambiguity. And the third is a parameterization issue that becomes very important when we tackle large real-world scenes, like the kinds of unbounded scenes, large outdoor environments, as you saw in the Freeview synthesis videos and the tanks and temples dataset. Let's start with these first 2 issues, the 2 ambiguities, the shape-radiance ambiguity and the near-field ambiguity. And these 2 issues can be traced to one fundamental factor. That factor is NERF is over-parameterized. NERF represents the radiance field with 5 parameters. The space of rays is 5-dimensional after all. But many of you may recall that the classic representations for radiance for the planoptic function in computer graphics used 4-dimensional parameterizations. These were 4-dimensional constructs. Why is that? Well, the reason is that the intrinsic dimensionality of the radiance field is more like 4 than 5. It is a somewhat ambiguous construct, but I think we can say with some confidence that the intrinsic dimensionality of the radiance field is closer to 4 than 5. Why is that? Well, first of all, look at the modeling decisions made in the classic, in these classic representations of the planoptic function in computer graphics. If you look at, let's say, an image plane, okay, a plane through which you want to view the scene, the space of rays that cross this image plane, that emanate from this image plane, clearly becomes 4-dimensional. So this is obvious. This is basic geometry, and that is the root of the 4-dimensional parameterizations adopted by prior representations of the radiance field. But what about whole scenes, you might say? I don't want to just view the scene through a plane. I want to travel freely through the scene. What happens then? Well, what happens there is a very important, a critical, fundamental property of radiance, which is that radiance is constant along a ray that travels through free space. So, as a ray travels through free space, radiance is constant. So you might think that there is a degree of freedom there. You are traveling along a ray, so you are changing something. There is a degree of freedom. This degree of freedom is in some sense illusory. It's redundant. There is no freedom. The radiance is constant. Nothing changes. As you travel along a ray in free space, nothing changes. So the interesting events where radiance actually changes, if you don't have participating media, are along surfaces of objects. So surfaces of objects are 2-dimensional. So the origin can be parameterized by 2 dimensions. The direction of the ray gets 2 more dimensions. We get a 4-dimensional manifold. The radiance function, the informative part of it, the interesting part of it, where something actually happens, is really a 4-dimensional manifold. The rest is basically determined by this 4-dimensional manifold. And what we will see is that not modeling this constancy of radiance, this radiance constancy along rays, has serious deleterious consequences. It has serious drawbacks in that NERF has, in some sense, too much freedom, too much expressivity for its own good, in that it can fit the training objective absolutely perfectly and at the same time hallucinate a completely incorrect solution, a solution that's arbitrarily wrong, while fitting its training objective perfectly. So let's see this in action with the shape-radiance ambiguity. Consider two rays from two cameras that see the same point, for example, on our lovely teapot. And you might imagine that the following happens for a well-trained nerf. You step along each of these rays from the camera, you sample, you'll get density 0 while you're sampling in free space, and then you hit the surface of the teapot and you get density 1. Okay, that's what we want nerf to learn. That's what we imagine it learns, and indeed it can learn that. That would be a valid solution that would fit the training objective perfectly. But there is also an infinite continuum, an infinite space of arbitrarily wrong solutions that will also fit the training objective perfectly. Here is one of them. Instead of the teapot, let's just hallucinate that the geometry of this scene is a perfect sphere. And there's nothing special here about the sphere. It can be when the ray hits the sphere, and the radiance along this ray will be correct. It will be what it needs to be to match the training image from this camera, and likewise from this camera. In this way, we can fit the training objective of nerf with this arbitrarily wrong solution that has nothing to do with reality perfectly. We can drive the training objective to 0. Again, this goes back to this extra degree of freedom and this extra expressivity in nerf that can be abused, that allows nerf to be deceived, to deceive itself. Of course, the deleterious consequences are that even though images, you go into new poses, the appearance of the scene will shatter. It will break down completely. What you'll start seeing overfit perfectly to the training images, but it is incredibly brittle. Since the underlying estimated geometry of the scene is completely wrong, once you start moving the camera away from the training poses, you will see just really horrible results. And we can reliably invoke this in controlled experiments. This does happen. We can invoke this on demand in controlled experiments. This is real, and we can reproduce this basically at will. Now, in fact, the relevant question becomes, since it's so easy for nerf to be deceived, and it's so easy to drive the training objective to 0 with an arbitrarily bad solution, the next interesting question is, why does nerf ever work? Why does nerf work at all? Why does it, in fact, ever find the right solution and not any of these infinitely bad solution, any of this infinity of bad solutions that would also fit the objective? And this has to do with a decision made in the implementation of the nerf approach that is rarely discussed and seems to be underappreciated, which is the following. This, from my description so far, is what you might think NERF is doing. It feeds some representation of the ray, the origin and direction of the ray. By the way, NERF uses a clever encoding of the ray parameters into Fourier features. This is actually orthogonal to the point we are studying here. So that encoding is nice, useful, and clever. But that is not the point here. It is important, it's good, it helps improve the results, but it's completely orthogonal to the point we are making here. So, NERF feeds some encoding of the ray parameters, encoded as Fourier features or whatever, into a multi-layer perceptron, and you might think that this is what's happening, and then it produces this multi-layer perceptron, outputs the color and density. That's what you would think from my description so far, and I think this is what many people think is happening, but that is not what is happening. What's really happening is actually extremely important. It's very different, and this difference is extremely important. What travels through the bulk of this multi-layer perceptron is just the origin of the ray, the encoding of the three spatial coordinates. So the vast majority, the bulk of the NERF network is not view dependent at all. It has only 3 degrees of freedom, not even 4, 3 degrees of freedom. The other 2 degrees of freedom, the view dependent branch, start here. The view dependent path begins here in the penultimate layer and basically goes through a single layer. The ray direction, which are these extra degrees of freedom that NERF can use to basically fail arbitrarily badly and encode a completely incorrect hallucinated geometry to fit the training data. That is, those degrees of freedom are fed to the network only at the very, very end and go basically through 1 or 2 nonlinearities, depending on how you look at it. Let's say 1. It's an extremely shallow subnetwork that is starved of capacity. So what's happening here is that there is a structural regularization, an implicit regularization that is rarely talked about, but is in fact critical of starving the network of capacity, such that the network simply doesn't have enough capacity to overfit the data. This is very important because if you follow the general program I described earlier and you do something like this, the failures of NERF really multiply. The shape-radiance ambiguity becomes really a big problem and much easier to invoke. So it's important to remember that this rarely discussed and unappreciated structural implicit regularization actually is one of the most important decisions in making NERF actually work when it does. A related ambiguity that also harnesses this over-parameterization of NERF and basically preys on the extra degree of freedom that NERF has is the near field ambiguity. And the near field ambiguity is another way in which NERF can cheat to perfectly fit the training data while hallucinating completely incorrect geometry, completely incorrect scene structure, and failing to generalize completely. And the basic idea is that in the near part of its view frustum, for example, look at this camera, there is a part of its view frustum that is not observed by any other camera, that is not triangulated by other cameras. And in this part of its view frustum, NERF can easily just hallucinate the training image. So during training, NERF, in the extreme, for example, can just put a little billboard with a painted training image on it, right here in front of the camera, and be very happy. It can just hallucinate the training image right in front of the camera and be perfectly happy and fit the training objective absolutely perfectly, drive the loss to zero, and of course completely fail to reconstruct the scene such that when the camera moves, the image breaks down completely because NERF hasn't learned anything useful. The third issue that we analyze and aim to rectify in our work is the issue of parametrization. The issue here is that NERF parameterizes the entire scene essentially in a compact volume. Let's say, for simplicity, a unit cube, a 3D unit cube. So the entire relevant volume of the scene is projected to a unit cube, and this is the domain over which the multi-layer perceptron is trained and estimated. This is the domain to which the multi-layer perceptron allocates its capacity. This creates a problem when the scene has very high spatial dynamic range. So, for example, if you have foreground objects that are right in front of the camera, that are viewed in great detail, where it's very important to estimate this detail, let's say 1 meter, 2 meters from the camera, that part will be allocated capacity along with the rest of the scene. But what if the rest of the scene is actually huge? And it's also important that we actually see this rest of the scene, because the camera can look at it and see tens of meters, hundreds of meters, maybe a kilometer away. So what we see in many real-world capture settings is that there are objects in the foreground and front of the camera, objects of interest that need to be reconstructed in great detail, but the camera can also see past them. And there is a backdrop that's maybe hundreds of meters away, but it's also very important that we see that at the appropriate level of detail. And NERF must trade these off because it has finite capacity, it has a finite sample budget, it has a finite training time. If you look at the details, if you look at its structure, and what happens in practice is, if the foreground part of the scene is allocated a lot of capacity, then the background ends up reconstructed poorly and is blurry. Whereas if we somehow project the whole scene into this unit cube over which the multi-layer perceptron is trained and operates, then the background might be a bit better, but then the foreground is very blurry. So there's kind of a zero-sum game that is happening because finite capacity is allocated over a scene that's potentially very large, and with even more important than absolute spatial extent, it may have very high spatial dynamic range. We discuss a number of solutions in our work that make NERF work better, and this is what we call NERF++. To guard against the shape-radiance ambiguity, we introduce acute auxiliary loss that helps NERF steer away from the poor solutions that misestimate the geometry of the scene. To guard against the near-field ambiguity, we introduce an adaptive near-field culling that culls the front part of each view frustum adaptively based on the geometry of the scene, and tries to disallow estimating geometry right in front of the camera as the vanilla nerf is liable to do. And then finally, to handle the parameterization issue in the original nerf, we introduce a neat homogeneous parameterization that allows you to have high detail reconstruction in the foreground as well as detailed reconstruction of the background. Now let me just show you this homogeneous parameterization because it makes a big difference in practice, and it's actually very simple. The basic idea is that we train two nerfs. One nerf for the foreground, part of the scene that is designated as the interior, the foreground part of the scene, that is enclosed by a sphere. Let's just change the scale for convenience. So this is the unit sphere. This is a compact region. We can just train the nerf with its basic parameterization for the compact region. The entire scene outside this sphere is reprojected. It's folded into a four-dimensional unit cube. And this is a very simple reparameterization. This is a very simple reprojection that basically folds the unbounded three-dimensional space outside the unit sphere into a higher dimensional, into a four-dimensional unit cube. Note that there does not need to be any scene boundary at this unit sphere. It really doesn't matter what actually happens in the scene at this unit sphere. You will not see the boundary. The way the approach is structured, you will not see a boundary when you render the scene, but you simply cleverly allocate capacity to a foreground region where the camera is more liable to look at objects closely and examine them in detail, as well as the background, which you want to be there and you want to synthesize and you want it to be sharp, but doesn't need to be modeled at the same level of spatial detail. Let's look at some results and let's compare nerf++ with these ideas to the baseline nerf. Let's look again at the truck scene. These are the input images from the Tanks and Temples truck scene. And here is a comparison of nerf and a nerf++. In parenthesis, I put the PSNR for each approach. And you see that nerf++ gains 2 decibels in PSNR. And this 10% improvement in PSNR, in this case, is very significant. It corresponds to very clear differences in visual quality. The truck is sharper. You can see the writing on the side of the truck. You can see the details on the wheels. You can see the sign on the back much more clearly. The background is better preserved. The whole scene is really quite a bit better, and you see it even more clearly when you view the videos at high resolution. So we really have done something here. Here is another Tanks and Temples scene. This is the train. Here you again see the input images just so you can see what the scene itself looks like and what input was provided to the different techniques. And here are the results of nerf and nerf++. Again, you can see the writing is much sharper. You can see the surface of the train at much better detail, and you can see the background much better as well. Note that we really went out of our way to make the vanilla nerf work as well as possible and to make the comparison as fair as possible. First of all, you will notice that the sequences that I'm showing here for the vanilla nerf are better than the sequences we showed for nerf in the free view synthesis comparisons. Why is that? The main reason is that nerf++ has twice the sample budget of the vanilla nerf. Because of this homogeneous parameterization, we are in effect training two nerfs. Each nerf gets the baseline sample budget, but the two nerfs together, which comprise nerf++, get twice as many samples. So, to make the comparison maximally fair, to equalize the samples and the training time and the capacity given to nerf and nerf++, we also train the baseline nerf for twice as long with twice as many samples. We give it the same sample budget as nerf++, which is twice as high as the settings for the nerf, the baseline settings for nerf that were used in the free view synthesis comparisons. That alone makes nerf work better in these new comparisons that I'm showing you. And we also really went out of our way to tune the hyperparameters basically manually as well as possible to really make the vanilla nerf work just as well as possible with extensive manual hyperparameter tuning. So the vanilla nerf results here for these reasons are better than the vanilla nerf results you saw in the free view synthesis comparisons, but still they are clearly not photorealistic and clearly not great. And nerf++ is much better. Here is another scene. This is the playground scene. Some input images. And here again is the comparison of nerf and nerf++. Nerf on the left, again you see it's quite blurry. Nerf on the right, you will see it's sharper both in the foreground and in the background. It's not quite perfect, actually it's far from perfect. Photorealism has not been attained, but it's really quite a bit better. Finally, let's look at the M60 sequence. Here are the input images again. And here is nerf and nerf++. Again, the original nerf is quite blurry. Not a complete failure at all, but definitely not photorealistic. The nerf++ on the right is much closer. Still not perfect, but clearly quite a bit sharper, quite a bit more realistic. We can make out the details much better. I want to close with some broader discussion of the approaches that we reviewed today, the trade-offs between them, the outlook into the future, and some closing thoughts on the pursuit of photorealism. Let's begin with analyzing the runtime of the two approaches we saw today, because it is another factor that is quite important, but not commonly discussed, it seems, and somewhat underappreciated. Both nerf and nerf++ require per scene training. This per scene training takes, in our experiments, about 3 days per scene on a high-end GPU, on a 2080 Ti GPU. 3 days for a single scene. Note that here this is with the higher sample budget and the higher training time that we used for the nerf and nerf++ results that I showed you over the last few minutes that were really maximized for just maximal visual quality. You can reduce the training time, but that will hurt the visual quality. So to get the visual quality that I just showed you over the next few slides, that takes about 3 days of training per scene on a high-end GPU. Free view synthesis does not train its networks per scene. The networks don't need to be fine-tuned for a new scene, but It does run multi-view stereo and surface reconstruction. Those take time. They take about 2 hours for a representative scene in our experiments on the same hardware. So the comparison is about 3 days of per scene training for NeRF and NeRF++, and about 2 hours for per scene investment by free view synthesis for running multi-view stereo and surface reconstruction. All the approaches rely on structure from motion to localize the cameras for the input images. That takes about 10 minutes. So that is very reasonable. So those 10 minutes, I think everybody is pretty happy with. But the per scene training is an issue. We can of course assume that the implementations have not been exhaustively optimized, then you could perhaps gain an order of magnitude in performance with further investment, but these costs are substantial. Furthermore, let's look at the runtime of synthesizing an image with each of the approaches. So synthesizing an HD 720p image with NeRF and NeRF++, again with our settings, with the higher sample budget, hyperparameters set for higher visual quality, takes about 1 to 2 minutes on the same high-end recent GPU, on a 2080 Ti GPU. 1 to 2 minutes to synthesize a single image. Free view synthesis takes roughly 1 second to synthesize an image. That second is spent on doing forward passes in the encoder and decoder networks and reprojecting the features from the nearby input views to the target view. It's safe to assume that neither of these two implementations have been optimized for high-speed, high-rate image synthesis. I think it's reasonable to assume that there is an order of magnitude that can be gained with less than a month of work by just optimizing these. But right now, the two approaches, the image synthesis time differs by 2 orders of magnitude. So if we gain that 1 order of magnitude with dedicated optimization, FVS would probably enter the interactive regime, will probably be at 1020 frames per second, whereas NeRF and NeRF++ will probably go down to on the order of 10 seconds of synthesis, or at least multiple seconds per image to synthesize one image, which is still quite far from real time and quite far from satisfactory. Again, an aspect that that seems to be underappreciated at the moment. As I mentioned, the two approaches are actually quite different in their philosophy. Free view synthesis is quite modular. It leverages components that are of independent interest and have independent momentum behind them, and communities that are devoted to advancing these components, like multi-view stereo and 3D reconstruction. NeRF and NeRF++ are more radical and involve a more fundamental reconsideration of the view synthesis pipeline. And NeRF was interesting to us for that reason. We wanted to understand this radical approach better and understand the trade-offs and how far it can be pushed. One note I want to make is that there is a common misunderstanding here about end-to-end and its relationship with modularity. A common misunderstanding is that there is a kind of dichotomy between end-to-end training and modular design, that either you have a modular system or you have end-to-end training. In reality, there is no such dichotomy. End-to-end training is perfectly compatible with modularity. You can have a modular system and you can do gradient-based training such that in the very least the later modules adapt to the performance characteristics of the earlier modules. So in free view synthesis, for example, the neural rendering module can adapt to the drawbacks and can in part compensate for the drawbacks of multi-view stereo and surface reconstruction. Of course, some of those drawbacks may be too severe, and the later module may just not have the structure, the expressive power to completely, perfectly compensate for the drawbacks if the earlier module fails. But end-to-end training is possible, and adaptation to the failures of earlier modules is possible. So a failure or a limitation of an earlier module need not result in a complete collapse of the whole system. Free view synthesis is designed to essentially ride on future improvements to multi-view stereo and surface reconstruction. Here you can see the Tanks and Temples leaderboard that shows the progress in multi-view stereo that has been made just over the last 2 years. And you see hundreds of approaches on the leaderboard pushing the performance of multi-view stereo. And this is significant. There has been real progress in multi-view stereo in the last 2-3 years. This is real. The numbers have moved substantially, and the numbers actually mean something. The reconstructions really are getting better and better and better by the year. The most important general thought is that both methods presented today are far from perfect. Neither attains the level of photorealism that I think we should be striving for. We are far from done. There are glaring artifacts in the results of both approaches. Glaring artifacts remain for both approaches. You can see them even here at half resolution on this slide when the approaches are compared side by side, and you can see them even more clearly when you examine the results full screen at high resolution, which I encourage all of you to do. Now, which is which? Can you guess? Which is the result of free view synthesis, and which of these videos is the result of NeRF++? The video on the left is the result of free view synthesis. The video on the right is the result of NeRF++. In parentheses, you see their PSNR, and you see that it's comparable. The artifacts in the two approaches are different. They don't make the same mistakes. They introduce different artifacts that end up balancing out the numbers. My most important message for you is that there is plenty of work for you to do if you want to enter this area and help us drive towards photorealism. There are plenty of interesting problems we are not done, and plenty of deep and interesting work remains to attain the level of photorealism we are striving towards. A final thought is that neither of these view synthesis approaches presented today gives us the level of control over the scene that physics-based methods provide. With physics-based methods, the scene is interactive. We can move objects around, we can animate them, we can change the lighting, we can just engage with the scene, reconfigure it interactively, and do anything we want with it. Whereas the view synthesis techniques presented today really only allow us to walk around the scene that is frozen in time. They allow us to watch, to view a scene as it was when the original images were taken. The scene cannot be manipulated. We cannot really engage with it and modify it and reconfigure it. And this is a big drawback of these approaches, and a very exciting opportunity for future work that I think is very important and would be great for all of us to engage in. And I will reiterate my belief that the ultimate solution to photorealism will marry physics-based and image-based techniques. The ultimate solution will be a union, a synergy of physics-based and image-based ideas. And as evidence, I will again play a clip from this beautiful computer-generated short by Alex Roman that has been inspiring me for more than a decade now, because this clip has attained, in my view, photorealism. This is photorealistic, and yet we can engage with this scene. We can manipulate it. We see a realistic simulation of light transport in this scene, and we can see the amazing level of quality, the sharpness, the detail, and this is the sharpness and the clarity of appearance that we should all strive for. Thank you very much for your attention today.
I'm muted. Okay, now. Thank you very much, Vladlen, for this great talk. The talk was pre-recorded, as it's hard to appreciate the photorealism of the results that Vladlen was showing us through a live Zoom session. What I forgot to mention in the beginning is that, of course, you can also ask your questions through the Discord chat. So if you have additional questions, please go and type them into the Discord chat. I see some of you already did, and Vladlen is here live with us now to answer the questions from the West Coast. Yeah, so let's scroll up and start. The first question, amazing talk. The video shows horizontal parallax only since the observer is walking. So this was a question asked during the first part of the talk, the free view synthesis part. Do you have examples of view synthesis with full parallax, where you move into other directions?
Yes, we have evaluated on the DTU data set, which is more of a hemispherical arrangement of cameras, and we have both interpolation and extrapolation splits between the training and the test images on the DTU sequences. The details are in the paper, and our data is also publicly released in our GitHub repo. And DTU is a good example of full parallax along both latitude and longitude.
Another question from Katja. Thanks for the great talk. The original NERV results in NERV++ look a lot better than the results from NERV presented in free view synthesis. I guess that is a question you have already answered during the presentation. Okay, so let's go to the next one. For Vladlen, what do you think are still the remaining open problems in NERV++?
Yeah, well, we're not quite at photorealistic quality on large unrestricted outdoor scenes, and that to me is the first milestone we need to reach. We need to understand how to scale this very interesting and quite radical approach, as I said in the talk, to handle large scenes with outdoor, unconstrained, naturalistic capture. I think if we can do that, the approach is in very good shape. The next step after that is to make this scene interactive, reconfigurable, to move towards where we're at with the classic graphics pipeline, where objects can be animated, objects are functional, objects respond to forces, and that will probably be the next phase of work.
Thanks. So I'm just reading the next question. Martin Fuchs says, thanks for an inspiring presentation. In your motivation for NeRF++, you point out that the 5D planoptic parameterization of rays is wasteful and motivate a 4D light field / lumigraph parameterization. The main difference between planoptic and light field rendering is that light field rendering is constrained to rays outside the scene. Can you still step inside the scene with NeRF++, and what happens when you do?
Oh yeah, so NeRF++ is 5D. It has the same flexibility, the same freedom as NeRF. To be clear, I always found the 4D plane-based parameterizations of the light field and the lumigraph too restrictive. They are designed for either viewing the scene from a kind of virtual window or looking at an object from outside. It's not a convenient parameterization for walking through a complex scene. In this sense, the 5D NeRF parameterization, the parameterization that NeRF adapts is much better. It's much more convenient. So I do like the 5D parameterization a lot. It could be nice if we figured out how to regularize it, to perhaps build in some priors that we know about physics and light transport and how real-world light transport behaves, such as radiance constancy in free space. Also, I probably should say that I probably overstressed the 4D versus 5D distinction a bit in the talk. Some of the issues that I described, some of the ambiguities that I described can be invoked also with the 4D parameterization. So some of these ambiguities do exist already with the classic 4D parameterization, and the 4D parameterization has its own issues and never quite took off. So I do like the flexibility of the 5D parameterization.
Good. The next question is by Patrick Wenzel. He asks, thanks for the great talk. What is necessary to make the algorithms generalized to unseen scenes? Could synthetic imagery potentially help?
You could try. Currently, NeRF is heavily tied to training per scene. You really are fitting this radiance field to a given scene. This seems to be built quite deeply into the approach, and it doesn't seem easy to imagine a NeRF that somehow gets maybe some images of a new scene as input at test time, and then maybe just in a forward pass interprets the data and produces a radiance field or produces a new image. It would be a kind of a hyper network kind of approach. It's conceivable, I guess, but not the way it works now, and doesn't seem very easy to make work.
So there's a question also from Hendrik Lensch. Very nice video, thanks. What is the main limiting factor? What is the main limiting factor concerning sharp reconstructions?
Well, the network needs to be expressive and expressive in the right way. So the network approximates a function, right? It's a function from a 5D space, the space of rays, to the space of colors and densities. So this function has, the real function that is being approximated has a certain geometry. It has certain geometric properties. The function approximator we use has to match these properties. The frequency distribution that the function approximator can express needs to match the frequency content of the function that we are aiming to approximate, right? So that needs to be in alignment. We don't fully understand what is the frequency content of the function we are approximating of the real radiance field. The fact that it's in 5D doesn't help because we can't just look at it. So the structure of the network needs to match the function that we are trying to approximate. I think once we get there, once we understand what the right structure is, we should be on a pretty good track. We need networks with sufficient capacity. They should have the right training objectives, and ultimately it comes down to an optimization problem. You need to drive the function approximator into the right mode so it actually fits the right function.
Thanks. There's another question from Torsten. Thank you very much for a great talk. One problem for neural rendering from neural viewpoints is how to render regions that have not been observed in the training images. Do you think having a sufficient amount of training data, whatever this is in numbers, can help solve this, or is there no hope to handle this problem?
There's definitely hope, right? Because we can do it. Humans can do it. We can imagine occluded parts of scenes. So if humans can do it, then we can build artificial systems that do it. It seems that the way we do it is that we have general knowledge from past experience about the structure of real world scenes. That kind of general knowledge can be present in neural networks. So you could train a network on a large distribution of scenes, a large distribution of radiance fields, and then somehow try to carry that knowledge over to a new scene. For example, you might fine-tune this big network trained on a whole set of scenes to a particular scene so that it retains its knowledge, its prior, and applies it to a new scene. This is actually a very interesting direction. It would be a very interesting project. It seems doable and would be a very interesting result.
There's one question by Katrin Lasinger. Comparing NeRF++ and free view synthesis, how many camera views do they need to reconstruct the scene? Does one of the two methods require more views than the other? And how far away can you move from the original views?
Yeah, great question. So in the comparisons that I showed, in the results that I showed, the exact same train test splits were used. The exact same sets of training images were used. So the methods were directly comparable. They were trained on the same data. I don't remember the exact number of training images that were used per scene. You can look at the free view synthesis repo. The data is public there. My general recollection, it's maybe on the order of 100 training images per scene, something like that. How far can we move? The answer to that question would be different for the two approaches. For free view synthesis, in principle, you could move reasonably far because the multi-view stereo scaffold should be reasonably good, as long as you're looking at a region of the scene that is represented well in the multi-view stereo reconstruction. Then there should be hope for producing a good image. You need some training images such that features from them can be reprojected into the target view. So you should be in the general neighborhood of training images, such that some training images can be retrieved and features can be reprojected via the MVS scaffold into the training views. I feel like in the future we should have a quantitative answer to your question. Your question is very good, and so far our answers are primarily qualitative. So in the sense we're at a fairly early stage here, but we should come up with quantitative answers for how far you can confidently move while retaining certain image quality. With NeRF and NeRF++, it's a little bit mysterious. So I don't think we have a really good answer, or right now a really good methodology for deriving an answer to your question. What kind of image quality can we expect from this NeRF at a given pose? So it would be really great to have machinery for answering this question. Like if I query the NeRF we trained at this particular pose, that my PSNR is expected to be 17 with a standard deviation of 1. Right, that's the kind of answer I'd like to get from the trained model. We do not have the ability to ask these kinds of questions now, and that would also be a very interesting project.
Thank you. There's one question by Bernhard. Says the methods showed only focus on the camera on captured objects. Do you think it's also possible to look around, turn the camera angle away from the main object, or will these methods then break if you don't have this kind of object focus as in the results that you have shown?
So you need to look at things that were clearly looked at, clearly seen in the training images. We don't have, as I mentioned, really great machinery for hallucinating unseen content. Right now in these scenes, it's possible, it's conceivable, humans can do it, but that's not what the approaches do right now. You need to, for something to be rendered well at test time, when you move the camera at test time, it needs to have been seen clearly and from multiple viewpoints. It also needs to be triangulated well. For the geometry to be reconstructed well, in the FVS approach, the geometry is reconstructed explicitly. In the NeRF approach, the geometry is reconstructed implicitly. For that geometry to be reconstructed well, the surfaces need to have been seen from different, distinct objects so that the geometry can be triangulated. If that happened, then you should be able to look at the surface at test time, and you should demand to see it at good quality.
Okay, so the next question I think we can skip because you have already answered it, at least in parts. There's one more question. Thank you for the talk. Are view synthesis and 3D reconstruction similarly limited? So the question is basically, do you think like both view synthesis and 3D reconstruction suffer from the same difficulties and limitations?
I think at some level, yes. The answer is yes. I think there's no magic. So we can see that NeRF and NeRF++ actually do rely on triangulation under the hood. They don't do explicit geometric reconstruction as MVS methods do, but they really actually do under the hood. It's just implicit, and it's just hidden inside this procedure. But you need triangulation, right? There's no magic. If there's no triangulation, then NeRF is completely unconstrained. If you have one view, it can hallucinate any occupancy field, just a completely arbitrary occupancy field, and generalization will break arbitrarily badly. The scene will basically look arbitrarily poorly once you move away from the training view. So the triangulation constraints are basically the same in multi-view stereo and in NERF. It's just the representation of the geometry is different, explicit in one approach, implicit in the other. Then you could say, well, maybe we don't need triangulation. After all, humans can estimate the geometry of the scene from a single view. That argument applies equally to multi-view stereo, classic explicit 3D reconstruction, or implicit approaches like NERF. If you start bringing in priors and in-painting occluded regions, you can do that with explicit approaches, you can do that with implicit approaches. So I think the two families of approaches are pretty much on the same footing, actually.
Mm-hmm. So let me close with a question of myself. So the results that you've shown are focusing on the light field primarily, right? So they don't, like these approaches are not able to alter materials or objects or the environment lighting, right? So they are pretty much constrained in terms of the, I mean, this is general to all these approaches in this area, pretty much constrained to the environment lighting that is provided during the capture of the scene. Where do you see, what are the difficulties towards like also being able to manipulate these aspects and capture these aspects in your view?
Yeah, that's where I think we should start integrating image-based and physics-based approaches. So my current view is that what we want from these image-based approaches is material appearance. Material appearance is really data-driven. There's no physics that will tell us how my table looks or how the wood paneled wall behind Andreas looks. That's not physics. That's data. That's just the way the world is. And the only way to get a really great representation of that is to just acquire it from the world. These are not equations. You just go and you take an image of the wall behind you, Andreas, and now we know what that wall looks like. Light transport is physics. We don't need to learn light transport from data. We know how light transport works. We know how radiance travels through space. So if we can acquire appropriate representations of materials, of reflectance distributions on objects, then we can put them in a light transport simulation. And then we can manipulate the scene at will. We can change the lighting, we can move objects around, everything is fantastic. And that actually was what was done in that clip from Alex Roman, for example, that I showed a couple of times during the talk, and you saw the results. The scene looks gorgeous. It's incredibly realistic because of the image-based materials, and you're in complete control. You can relight it. You can introduce additional objects. So that I think is where we should go.
Fantastic. So thanks again for being our keynote speaker at this joint conference. And there were a lot of discussions and a lot of interest in your presentation. So thanks a lot for presenting today. This concludes the session. And yeah, to the audience, see you tomorrow. Thanks. Goodbye.
Thank you. My pleasure. Bye-bye.